Hello everyone. Welcome to the fourth video of week 2. In this video, we will explain a first general principle to construct estimators for parameters, the so-called method of moments. Let us start with discussing some former examples which in fact are an illustration of this principle. Recall the height example from video 5 in week 1. We modeled the observed heights as realizations of independent random variables with the same model distribution. A histogram of the observations suggested a normal distribution as a model distribution, and we argued that the average height is a reasonable estimator for the parameter mu of this distribution. The heuristic behind this argument is that mu represents the expected value of the normal distribution and, motivated by the law of large numbers, the sample average will be close to the expected value. You may also recall that the parameter sigma squared was estimated by the sample variance. And although we did not mention this at the time, the heuristic behind this is similar. Let me try to explain this. Recall that the parameter sigma squared represents the variance of the normal distribution. Therefore, if x is a random variable with this normal distribution, then sigma squared is equal to the variance of x. From probability theory, you have learned that the variance of x can be written as the expectation of x squared minus the squared expectation of x. Now we have already seen that the sample average x bar is close to the expectation of x. And for the same reason, the average of the squared observations will be close to the expectation of x squared. Combining these two means that sigma squared must be close to the following expression. Now you may check as an exercise that this expression can also be written as the following summation. On the right-hand side, you will almost recognize the formula of the sample variance, although here we divide by n instead of n minus 1. The reason to divide by n minus 1 instead of n is to obtain an unbiased estimator for the variance, as you have learned in the previous video. However, for larger n, this difference is negligible, and we find that the sample variance is also close to sigma squared. Now, the guiding principle that is used in the previous examples is that expected values of the model distribution are close to the corresponding averages of the observations. Different expected values are called moments. The expectation of x1 is called the first moment, and the expectation of x1 squared is called the second moment of x1. In general, the kth moment of a random variable x is defined as the expectation of x to the power k. And the average of observations in the sample are named similarly. The sample average is called the first sample moment. The average of the squared observations is called the second sample moment. And in general, the kth sample moment is the average of the observations to the power k. Now consider the following example. Suppose that we have observations that are modeled as realizations of independent random variables with an exponential distribution with unknown parameter lambda. The estimate for lambda can be found by the following procedure. Step 1 is to express the first moment of the model distribution in terms of lambda. Step 2 is to set the first moment equal to the first sample moment. And step 3 is to solve the parameter lambda from this equality, which leads to the estimator 1 over x bar. Now this principle can be generalized to what we call the method of moments. Suppose that the model distribution is characterized by one or more unknown parameters. Then we start by expressing the moments of the model distribution in terms of the parameters. then set them equal to the corresponding sample moments, and solve the parameters from the equations. Now, in setting up the equations, we use the following guidelines. Firstly, if the model distributions has more than one parameter, then we need more than one equation to solve for the parameters. For example, when the model distribution is a normal distribution, it has two parameters, mu and sigma. In such cases, we need to express multiple moments in terms of the parameters. And usually we need the same amount of moments as the amount of parameters to estimate. Well, let us determine the method of moment estimators for mu and sigma squared. Using the well-known rule for the variance, we find two equations in mu and sigma. Now next, we set the first two moments equal to their corresponding sample moments. And we can easily solve the parameters mu and sigma from these two equations. Now, since both equations need to hold at the same time, we can insert x bar for mu hat. And as we have seen before, the last expression can also be written as the following average. In this way, we have found the method of moment estimators for mu and sigma squared. It is often the case that several moments can be expressed in terms of the same parameters. And the second guideline is to use the smallest value of k for which the kth moment contains the parameters. For example, suppose that the model distribution is an exponential distribution. Then the first moment is 1 over lambda. Setting this equal to the first sample moment gives 1 over x bar as estimator. Now on the other hand, the second moment is 2 over lambda squared. And when we set this equal to the second sample moment and solve for lambda, we would find a different estimator. Now, as a convention, we take 1 over x bar as the method of moment estimator for lambda. Here's another illustration of the method. Suppose that we have a dataset of which the observations are modeled as realizations of independent random variables with a normal distribution with mean 0 and unknown variance sigma squared. In this case, the first moment is equal to 0. And this means that we need a higher moment to express things in terms of the parameter sigma. Now for the second moment, we again use the rule for the variance. When we substitute the values for the variance and the expectation, we find that the second moment is equal to sigma squared. We set this equal to the second sample moment and solve for sigma. And this gives us the method of moment estimator for sigma. Now let me finish by returning to the serial number example, where the estimation problem was simplified to drawing balls from an urn. In the second video of this week, you have learned that each random variable has the same discrete distribution, namely the values 1 up to k with equal probabilities. You have also learned that the first moment of this estimator is k plus 1 over 2. Now, according to the method of moments, we must set this equal to x bar and solve, which leads to the following method of moment estimator for k. Does this look familiar to you? Indeed, estimator 1 in the serial number example is the method of moment estimator. And estimator 2 in this example is linked with a second general principle that we will introduce in the next video. Now, for the moment, I invite you to have a look at the exercises in which you can practice the method of moments in a variety of estimation problems. Enjoy.